Hello everybody, welcome to this video which is about understanding OSPF concepts. This is in relation to chapter 21 of volume 1 of the official CCNA certification guide. So just a disclaimer in this video, unless explicitly stated, any references to OSPF are referring to OSPF version 2. So exam topics are going to be introduced in the next few videos, which is going to be an OSPF series. Are here. So this is from the official CCNA specification. So we're going to be looking at determining how a router makes forwarding decision by default, and so that includes longest prefix match, administrative distance, routing protocol metric. We'll get to all those things, and then configuring and verifying single area OSPF version 2. So neighbor adjacencies, point-to-point broadcast, designated router, backup designated router selection, router ID. So this lesson I've broken down to 7 sections. So the the first section is what functions do dynamic routing protocols perform? Interior gateway protocol and exterior gateway protocols. What is open choice path first? Actually defining what is open choice path, OSPF. Then 4 is quite a lengthy section, but this is 3 phases in order for OSPF routers to calculate and add best routes. So firstly is learning how OSPF routers become neighbors through the story of Charlotte and Samantha. 4B is exchanging the LSTBs between neighbors. And then C is calculating the best routes with SPF and adding them into the routing table. Number 5 is 6 rules to know for SPF areas. 6 is 3 types of LSAs we need to know about. And 7 is quiz. So that's 7 sections there. Now, I want to introduce to you guys 2 fictional characters that I'm going to be using in this lesson to explain some concepts. So meet Charlotte and Samantha. Charlotte and Samantha are neighbors and they're best friends. They live in San Francisco, California. So Charlotte and Samantha, a bit about them. They have some common interests. So Charlotte and Samantha both are avid readers, both love baking, and they both go to the same swimming club. So they are both swimmers as well. So these are some common interests that they share, and this is going to be important for later on. Now, what functions do dynamic routing protocols perform? This is the first section. So Cisco IOS supports several routing protocols, but they all perform the same 4 functions I'm going to mention now. Learning routing information about subnets from neighboring routers. Okay, we've got a router, and it's learning information about subnets that it doesn't know, that it doesn't previously know about from the routers that it has neighbor relationships with. So then advertising that routing information, telling other routers about it, about those routes. Hey, I learned this route. Pass it on. Tell the other routers about it. Now 3, if more than one route exists, select the best route using a metric-based calculation. And then 4, if the topology changes, react by advertising that some routes have failed and select a new best route. It's like if there's if you're driving down a highway and then there's a road closure, then if you're listening to the radio, you'll be those road closures will be advertised that, hey, such and such road is closed. So please, if you're heading on that, if heading down and you're about to get to that part that's closed, please divert, take a diversion and reroute your journey. They'll tell you take a different route to your destination. So these are 4 things that dynamic routing protocols all doesn't matter which one they are, they all perform these same general functions. So second section is interior gateway protocol and exterior gateway protocol. Knowing the differences is quite simple, but we need to know what an autonomous system is first. So an autonomous system is a network that's under the administrative management of a single organization. It could be an ISP, an internet service provider, it's a governmental organization, or an enterprise. An interior gateway protocol is designed for routing within an autonomous system, within that organization. An exterior gateway protocol is designed for routing between autonomous systems. So that's the difference there in a nutshell. So we're going to be looking at some interior gateway protocols now. So there's different types of interior gateway protocols. First, you got distance vector, then advanced distance vector, and link state. So open choice first is an example of link state. It takes into account the bandwidth of the interface. It takes into account the interface bandwidth for routing decisions. Now, if I also just mention advanced distance vector, this includes probably the best example of this is EIGRP, Enhanced Interior Gateway Routing Protocol, which is a Cisco protocol. It was a Cisco developed protocol. It was a proprietary protocol, but things have changed a bit. So I will explain that in the next slide. And then distance vector, an example is RIP, Routing Information Protocol, which used a hop-based metric where it would count the number of hops to make routing decisions. That was the only thing you looked at. How many hops from point A to point B? That's how it would calculate routes. It would calculate the best route using that metric. Now, timeline. Distance vector, by the way, is also known as Bellman-Ford, named after the inventors. Now, in the early 80s, distance vector protocols were introduced. Routing information protocols were very popular, and Cisco followed by coming out with their own proprietary protocol, Interior Gateway Routing Protocol. In October 1989, OSPF version 1 was released in RFC 1131. OSPF version 1, the first version. In 1992, intermediate system to intermediate system was standardized in ISO 10589, 10589. That was very important point in the history of IGPs. At some point in the early 90s, EIGRP, which was a Cisco proprietary interior routing protocol, was released by Cisco. OSPF version 2 was released in 1991. So not too long after the original version was released, version 2 came out that was described in RFC 1247. Then it was updated 3 times. RFC 1583 in 1994, 2178 in 1997, and then 2328 in 1998. In 1993, so whilst OSPF version 2 was being updated, in the midst of OSPF version 2 coming out and is being updating, OSPF version 3 was released, which included support for IPv6. That was released in RFC 2740. In 2008, 15 years later, it was updated in RFC 5340. And then RFC 7868, this was published in 2000. This was published in 2013. This was when EIGRP was made an informational RFC. So this was a big moment from becoming a proprietary, from going to starting as a proprietary protocol. It was published as an informational RFC. So that's a timeline of IGPs there. Now, IGP metrics, right? So I've touched on this in the 2 slides back. So RIP version 2, RIP version 2 uses a hop count metric to determine the best route. Now, it supports a maximum hop count, 15 hops. So you can't have a route with more than 15 hops in RIP version 2. OSPF, right? OSPF uses a cost-based metric based on the interface bandwidth. So what it does a calculation. Reference bandwidth, which is 100 meg per second by default, divided by the interface bandwidth. That's the cost-based metric. Now, EIGRP uses a calculation based on bandwidth and delay. So calculated based on the route's slowest link and cumulative delay for each interface in the route. So it's calculated based on the route's slowest link and cumulative delay for each interface in the route. So it uses a different metric there, and that's for that. And because of that, it's not a link state protocol. It's advanced distance vector. So it's not a distance vector. It's not link state. It's advanced distance vector. Now, so yeah, just to emphasize, ERGP was published as an information RFC in 2013. Number 3, what is Open Choice Path First? So OSPF, Open Choice Path First, is a link state IP routing protocol. It is an open standard protocol, so it's supported by various vendors, including Cisco, Juniper, and Palo Alto. OSPF has a few different iterations which are not interoperable. So namely, OSPF version 2 is not interoperable with version 3. These are like two separate protocols. If you've got a router with OSPF version 2 and a router with OSPF version 3, those two are not compatible. They're not interoperable because of those different versions of OSPF that are running on them. You can't use OSPF version 2 and version 3 and interoperate them. It does not work like that. You have to have version 2 on both routers or version 3 in both routers. Now, OSPF version 3 supports IPv4 and IPv6, while OSPF version 1 and 2 do not. It's something very, very important. One of the key differences between version 3 and version 2 and 1. This chapter will discuss OSPF version 2 only unless specifically I mention. Now, continuing on with OSPF. OSPF exchanges data about networks in, apologies for the typo there, data structures called link state advertisements. Link state advertisements exchange data about networks in data structures called link state advertisements. Okay, so a link state advertisement is a data structure. It's a data structure that holds topology information. Now, link state advertisements are collected by OSPF routers into a link state database, LSDB. Link state protocols like OSPF and intermediate system to intermediate systems, IS to IS, take on a task of flooding inter-network details in order to ensure that all the inter-networks have the exact same information as their own internet network. So, very important, I'm going to say that again. OSPF and IS to IS take on a task of flooding inter-network details in order to ensure that other inter-networks have the exact same information as their own inter-networks. They're doing that, taking on that responsibility to make sure that those other inter-networks have the same information or having the same information as they do. However, to stop bombarding routers with the same links to advertisements, to stop flooding the same links to advertisements and telling the router the same thing, the OSPF router will first ask the other router, do you already have this LSA? It's like receiving the same brochure again and again and again. Otherwise, it's like receiving that same brochure about a new pizza restaurant that's opened up down the road. You receive the same brochure every day in your mail. You're going to get really frustrated. You already know that this pizza place has opened. But you've received 7 brochures in the last week telling you about it. So to stop something like this happening, the OSPF router will first ask the other router, do you already have this LSA? Now, LSAs are reflooded when inter-network information changes, and there is an LSA aging timer, which will automatically reflood an LSA when the timer expires. So by default, an LSA aging timer expires every 30 minutes. So, two things there. LSAs are flooded when inter-network information changes. If a link goes down, a link goes up, then LSAs are reflooded. But also by default, when that time expires, and by default that's every 30 minutes. So that's 2 ways LSAs are being reflooded. There's a timer, and there's also when the inter-network information changes. So, jargon alert and a jargon buster here. We've got three terms here that I want to break down. So, designated router, DR. This is the route that all the other OSPF routers on an Ethernet link will sync their database with, their LSDB with. They're going to make sure that that router is the one that they are going to be syncing their database with. So the information that the designated router holds is like the master version of the data of the master LSDB. They want to make those other routers want to make sure that they have a matching LSDB to the designated router. Now, backup designated router is simply this is the one that will take over the designated router should it fail. And designated router other or druther or DR other, however you want to pronounce it. This means any router that isn't a designated router or a backup designated router. They are called DR other routers or other routers. So that's what these three terms mean there. Now, so we spoke about LSA flooding, and that's important to build an up-to-date LSDB. However, it isn't enough for deciding the best path. So what we need is the shortest path first SPF algorithm. So this was developed by the late computer scientist Edgar Dijkstra from the Netherlands. So Mr. Dijkstra developed this algorithm, and this is what is used for calculating the best routes. So now section 4. There are 3 phases that need to be gone through for OSPF enabled routes to start adding learned routes into their routing table. So firstly, we need to go through that process of becoming neighbors, passing compatibility requirements. Very important. To become neighbors, there needs to be compatibility requirements that are passed. Then exchanging the databases. And then number 3, calculating, adding the best routes. So we need to go through these phases in order to get to here, adding the best routes into the routing tables. So number 1, phase 1, compatibility between the neighbors. So now I'm going to be bringing those characters, Charlotte and Samantha, that I spoke about earlier. So when we look at human neighbors, right, they have compatibility requirements as well to become real neighbors, true neighbors, not just 2 people who live next to each other and never talk to each other, but 2 real neighbors, who get on with each other and do things together sometimes, and are look out for each other. Good neighbors, real neighbors. For humans to get to that position, there needs to be some sort of compatibility requirements as well. Now, they might be unspoken, but there have to be some sort of compatibility between those neighbors in order for them to be true neighbors. Now, so the main things are not causing a nuisance one another and having some things in common. I think that's what it comes down to. There could be more than this, but in my opinion, I think that's what this comes down to. Now, for example, Charlotte and Samantha are neighbors, right? So to not cause a nuisance, Charlotte should not park in Samantha's driveway. She should not play loud music at 2 a.m. when Samantha's sleeping, and she should not pick fruit off Samantha's tree. So those are some things that, in order to be compatible, they need to agree by some unspoken rules that you're not going to park in my driveway, you're not going to play loud music at the night, you're not going to take fruit off my apple tree in my garden. You're not going to do these things. Some unspoken rules of decency, of just human decency. So those are the unspoken rules, right? At the same time, they need to have some things in common. So shared interests, like being connected to the same swimming club or the same library. And so Charlotte and Samantha, they are members of the same swimming club. They go to the same library. They're avid readers, and they also love baking. So they have some interests in common. So that allows them to become neighbors. Okay, so there's some unspoken rules that they both abide by, and they also have some things in common that connect them to each other. So that is important for becoming neighbors. Now, routes also have compatibility requirements. So both routes need to be in the same subnet. They need to be connected to that same subnet. So for 2 OSPF routes to become neighbors, they must be connected to the same VLAN, same serial link, or same Ethernet WAN link. Same VLAN, same serial link, or same Ethernet WAN link. So I was speaking about human interests. Now, for me, human interests are like interfaces in a sense. The interests are what connect, because interests are what connect people, and interfaces connect routers. So for me, the interests are like the interfaces, right? Being connected to the same VLAN or the same serial link or the same WAN link. So what I'd say is, this for me is like how Charlotte and Samantha have some common interests. Some things that connect them to each other. So not interfaces, but it links the same serial link, same Ethernet WAN link, or the same VLAN. If the routers, two OSPF routers, are connected to either one of these, they can become neighbors. Like I was, and going back to the human neighbor relationships, Sean and Samantha they've got one or two common interests that enables them to be true neighbors. So I think these two things you can compare with each other, being connected to the same human interests, and connecting two neighbors together to become real true neighbors, and two OSPF routers being connected to the same VLAN or the same serial link, same WAN link, enables them, the same Ethernet WAN link enables them to be neighbors. But they also must declare some compatible OSPF settings, and this is like the unspoken rules I was talking about. So there's some compatible OSPF settings that they also need to agree on to become true neighbors. So this is what phase 1 is about, becoming neighbors. Okay, so now I want to talk about hello messages, right? Hello messages. So in that process of now becoming neighbors, a router begins begins the process of becoming neighbors by exchanging hello messages. Now, hello messages contain a 32-bit dotted decimal notation, DDN value, which looks like an IP address. Now, by default, iOS chooses one of the router's own interface IPv4 addresses to use as its OSPF RID. So by default, iOS chooses one of the router's own interface IPv4 addresses to use as its OSPF RID. So that's something quite important to note there. If you've got a notebook in hand and pen, please write this down. iOS chooses one of the router's own interface IPv4 addresses to use as its own OSPF RID by default. So the RID can also be manually configured. So to see brief details of OSPF neighbors, use the command show IP OSPF neighbor. Show IP OSPF neighbor. Please also write that down. So that's two things I want to specifically highlight. So let's go into the next slide. So very important, hello messages follow the IP packet header using the IP protocol type 89. It's also something important to know about IP protocol type 89. Now router 1 sends a hello packet to the new sends a hello packet to the multicast address 224.0.0.5, which all OSPF routers listen to, so that they can form new relationships. Okay, form new neighbor relationships. So route 1 sends a hello packet to the multicast address 224.0.0.5, which all OSPF routers listen to, so they can form new new relationships. This is your so if I was to give you an example, you got which is here, for example, here, this is router 1. Now those routers here are listening for these messages from this that are to this IP address 224.0.0.5. So multicast packets from designated routers to designated router others, DRO the routers, are sent using the reserved IP multicast 224.0.0.5. So these routers here want to form new relationships. So that's why they're listening to messages from this that are being sent to this IP this multicast IP address that's reserved. So that's 224.0.0.5. So router 1 here is the designated router I'm referring to here. That's the so this router is the designated router. That's why it says DR here. So going back to the slide, in becoming neighbors, routers go through different states. There's a state init, then there's a two-way state and a full neighbor state. Now we'll now take a look at an example of this happening in this video now. Hi guys, welcome to this video here where I'm going to be talking about how a router forms a neighbor relationship with another router. There's several stages that they go through. So if we look at this example here, we've got Charlotte's router and we've got Samantha's router. Now what happens is, here we have a link between Charlotte and Samantha's router. This link comes up and we pass through different stages in the process of becoming neighbors. So firstly, Charlotte's router sends a multicast hello message to out using the IP address 224.0.0.5, and that goes to all OSPF speaking routers. Now when Samantha's router receives that hello message, it sees, okay, router ID of Charlotte's router 11.1.1.1. Now what happens is, it goes this now means that we go into the interim beginning state of init, and that is Samantha's router is now in an init state. When Samantha's router sends its own hello message back to Charlotte's router, it sends its own RID, but it also mentions Charlotte's router's ID. So when Charlotte's router receive it, it sees, okay, I can see my own RID here being acknowledged by Samantha's router, and so this means Charlotte's router now goes into a two-way state, because that is one of the things that have to happen, is that the router needs to see its own RID being sent to it in a hello message by the other router. So this happens now for Charlotte, but Samantha hasn't, not on Samantha's side, so Samantha is still in an init state. However, when Charlotte now Charlotte's router sends a hello message next time, it says it includes its own RID and Charlotte's RID, and so now that puts Samantha in a two-way state, and when both routers are in a two-way state, they become neighbors. So that's an explanation there of the process of becoming neighbors. Now, if we now move into phase 2 of these three phases, maintaining neighbor relationships and the link state database. Now, in a nutshell, there are three maintenance tasks in this phase, right? So firstly, it's hello and dead interval timers. Now, the dead timer is 4 times the hello timer by default. Okay, so what this means is, hello messages are being sent, but there's a dead timer as well. So if a router, for example, Charlotte's router, like I was mentioning Charlotte and Samantha's router, if say Charlotte's router, we're talking Charlotte's actual router, not a Charlotte as a person, Charlotte's router was not receiving a hello message for such a long period that it becomes 4 times that hello timer. So let's say the hello time is 10 seconds. Let's say it was 40 seconds, not received a hello message. Now router, or Charlotte's router, is going to think that hey, there's something up here. I've not received anything, and for the 4 times the hello timer, so it stops using that. It assumes that this link is now it will not use that link anymore. It's not going to use that link. It's not going to send it. Is because that it determines that is not usable now. Samantha's router is not contactable. It's down basically. It assumes that it's down. So number 2 is flooding changed link state advertisements to each neighbor. Flooding changed link state advertisements to each neighbor. So remember what I mentioned about how if topology information changes about the internet network, then that is reflooded by a router to the rest, to the other neighboring routers, and that is what's happening. And also I mentioned any unchanged LSAs by default are reflooded every 30 minutes. So yeah, so that's just basically a repeat. So hello and dead interval times. Dead timer is 4 times the hello time by default. Flooding unchanged LSAs to each neighbor, and reflooding unchanged LSAs by default. This happens every 30 minutes. Now, I want to do some. I want to introduce this table now. So, which is talking about the neighbor and relationship terms, for the different states. So, a two-way state. The term for this is the term for this when we've is neighbor. So when you've got neighbor in a two-way state, the neighbor term is neighbor. The relationship term is neighbor relationship. So, for example, when we looked back at Charlotte and Samantha, and we saw that at this state here, Charlotte entered a two-way state. So that's what we would call so the neighbor term there is neighbor. However, it's not a fully adjacent neighbor or adjacent neighbor. It's not a full, we didn't reach that full neighbor state yet. That didn't happen until here. When both routers were in two-way state, then we entered that, what we call an adjacency, a fully adjacent neighbor or adjacent neighbor. So that's an adjacency. This is a neighbor relationship. So that's kind of the difference there. Now moving on. So database exchange. All show us first designated routers multicast message. All SPF designated routers multicast message. So there are two types of multicast messages in relation to OSPF, whereas a RIP and EIGRP use one each. So at least that's what's mentioned in the CCNA book, is that there's only one each for those routers mentioned, for the one each for RIP and EIGRP, but OSPF uses two. So when you got designated route, you got DR other routers, and they want to communicate to the designated router and the backup designated router, they'll use this multicast reserved IP address 224.0.0.6. So that is all SPF's designated routers multicast. It's going from the DR other routers to the designated router and also the backup designated router, because he needs to know this information, because one day he might become the designated router. He might have to step in. Now, I did go over this slide a bit earlier. So all SPF routers multicast. This is the opposite of the previous one. This is going from designated routers to the DR other routers, and thus using IP address 224.0.0.5. So don't get confused. 224.0.0.6 is from DR others to the designated router and the backup designated router, whilst 224.0.0.5 is from the designated router to the other routers, the DR other routers. So here we have it. OSPF uses 224.0.0.5 and 224.0.0.6. So .6 is from designated router so from DR other routers to the designated router and the backup designated router, whilst 224.0.0.5 is from the designated router to the DR other routers. EIGRP uses 224.0.0.10 and RIP uses 224.0.0.9. So those are three. Those are the multicast addresses. Sorry, please ignore that. 224.0.0.9, 224.0.0.10, 224.0.0.5, and 0.0.6 for OSPF. These multicast addresses being used by these three interior routing protocols. Now, default interface cost value for OSPF. So this is something important to remember. Now, when OSPF is trying to add up cost, OSPF uses these cost values for different interfaces. So gigabit into Ethernet interface, that's the cost value of 1. Low cost is always better. Fast Ethernet interface, cost of 1. Ethernet interface, cost of 10. DS1 or T1, which is used in North America and Japan, 1.544 meg per second. That's 64. That's a cost of 64. And DSL 768 kilobits per second. That uses a cost of 133. So these are default interface cost values for OSPF. Now, 4C, the last phase, calculating the best routes with the shortest path first. So, cost-based metric, OSPF uses this formula to calculate or to make its calculation. Reference bandwidth, that's 100 meg by default, divided by the interface bandwidth. So, for example, you've got a fast Ethernet interface, so that has a cost of 10. You've got a reference bandwidth, let's say you kept the reference bandwidth at 100 by default. So you got 100 divided by 10, that's a cost of 10. So as an example there. Now, when shortest path first identifies a route, OSPF calculates the metric for a route as follows. So the sum of the OSPF interface costs for all the outgoing interfaces in the route. All outgoing interfaces in the route, we add the costs for each of those hops there, for all each of those interfaces that are going to outgoing interfaces that are going to be that we're going to be hopping through. Those costs are added, and then that gives us the total cost of for that route. So, for example, you might have link A, B, and C. So for A, you had a cost of 20. B, you had a cost of 30. C, you had a cost of 40. And so, well, 20 and 30 and 40 is 90. So that's a cost of 90. But then you had a route with 2 links, and that had a cost of 30 and 40. That is cost of 70 when you'd use the second path there. So part 5, 6 rules of OSPF areas to know. So firstly, we need to configure all the interfaces connected to the same subnet inside the same area. Number 2, an area should be contiguous. 3, some routers are internal routers. So those are interfaces within a specific area. For the some routers are area border routers. So some interfaces connect to the backbone area 0, and some to non-backbone areas. All non-backbone areas must have a path to reach the backbone area. So that will be so here's where the area border router, the ABR, comes in. So there's some interface will connect to the backbone, some don't connect to the backbone, but this is connecting those areas with each other. Now, it's recommended to not connect more than 2 areas within an area border router to avoid overburdening the router. So how do OSPF areas then reduce the SPF calculation time? You might be wondering this. How do the OSPF areas reduce the calculation time? It's a very good question. So areas cut down the workload. Essentially, they cut down the workload. OSPF enabled areas routers contain LSDBs, only listing routes and links for their area, nothing more. So it's simple there. We only got the LSDB for the routes and links for that area. But hang on a second. You might be wondering, doesn't the router still need to know about other subnets for routing decisions? If that's you thinking that, you're absolutely right. The answer to this question is 4 words, which is summary link state advertisements. Summary link state advertisements. So these are what help us. This is what helps us know about other subnets. The router helps an OSPF enabled router to know about other subnets. Summary link state advertisements. But there are 3 link state advertisements that we need to know about here. The summary is the final one that we're going to talk about. That's type 3, but there's type 1 and type 2 as well. So type 1, this is router LSA. Okay, type 1 is router LSA. These describe router interfaces, IP address, subnet mask, current interface status, notes about its neighbors. Each router generates its own each router generates its own, not SLA, LSA. Okay, it generates its own LSA for that router. It will example, if you got router 1. Router 1 will generate its own link state advertisement. So these describe a router. If you will go back to the Charlotte and Samantha story, Charlotte and you could think of this as a piece of paper that that Charlotte can read about Samantha. So that will tell us her about Samantha's interests, and Samantha's will say Samantha's address and Samantha's current status. So if she's at home or she's not at home, and some of her thoughts and comments about her neighbors. So that I live across the block, for example. So across the street, sorry. So you could think of it as a piece of paper that describes a neighbor, the interests. So obviously address, name, interests, and whether they're at home or not, and notes and notes which tell you what their feelings are about other people living down the street. So just an analogy there. Link state advertisement type 2 network LSA. So these describe a network that has a designated router and a backup designated router. So these include designated router and backup designated router IP address. Okay, the IP addresses for the designated router and the backup designated router. Subnet ID, subnet mask. I like to think of this as a piece of paper which tells Charlotte not about Samantha this time, but Samantha's immediate family, her parents, her siblings. So that includes her parents' addresses and where they live as well, which is within the same, which is within San Francisco as well. So it's in the same. They live in the same city, but the obviously addresses are different. So I like to think of this as between a piece of paper that describes Samantha, and what I'm going to come on to next, which is going into Samantha's extended family to explain type 3 LSAs. So you got a piece of paper that describes Samantha. That's like a type 1 LSA. It just describes Samantha herself. Okay, like a type 1 LSA, it just describes the route. It just tells you about the route. But type 2 will tell you about the network that router belongs to, the designated router, the backup designated router, includes the addresses, subnet ID, subnet mask. So it tells you going into more information there. And then when we go into type 3, we got more information than that. Or if not necessarily more, it's going into a different level of detail now, a different information. So I like to think of this as about telling you about a router's extended family, because what a type 3 LSA does is it explains a summary LSA. They include the subnet ID and mask for a router that resides in another area. Okay, they don't include topology information, but they include the subnet ID and mask for a router in another area, and no OSPF processing is required for summary LSAs. So, in the summary LSA, describes the subnet in another area. Describes the subnet in another area. So you have subnet ID, the mask, the router ID of the ABR, the area border router, that advertises the LSA. The LSA of the type 3 LSA. So, if I were to use, so here we got subnet ID, mask, router, the RID, router ID of the ABR advertising the LSA. So, for example, when it comes to Charlotte and Samantha, if Charlotte invited Samantha to a large family gathering she was hosting, Charlotte would need to introduce Samantha to those family members, because she hasn't met them before. They don't live in San Francisco. She's never met them. So Charlotte will need to give Samantha a brief summary of the family. So, for example, Samantha, this is my Uncle Tom and Aunt Jane. These are my cousins. David, Joseph, and Kate, and they live in LA. So that gives a summary of who those individuals are, who that family is. So we can think of that as the subnet ID, who that family is, and the and where they live. So and that's like the area, because that's a different area, so to speak, than San Francisco. It's a different city, but in terms of if we're in the context of LSAs, that's like a different area to if San Francisco is the backbone area, then LA is area 1. San Francisco is area 0, LA is area 1. So that's a different area. So he needs to he will learn this through summary LS. You will know about this with summary LSA. So basically, summary LSA describes subnets to a router that doesn't reside in its own area. Like a summary of these families is telling Samantha about people she's never met before because they don't live in San Francisco. So it's a bit of a far-fetched analogy, but I think it helps to understand it through a bit of a story, that it's like you trying to... It's like... here, Samantha's learning about families she's never met before. But an important thing is, Charlotte in this story is like the area border router. Why? Because Charlotte is the individual who connects San Francisco and LA in this case together. She's connecting these two areas, and these two and her uncle Tom and Aunt Jane's family with Charlotte. She's that connection. She's that piece in the jigsaw which connects the two together. Like an area border router is what connects two areas together. The backbone area and a non-backbone area. It's that area border router that's doing it. It's the area border router. So I think it helps to understand it through an analogy like that. Now, benefits of multi-area OSPF. So multi-area OSPF, remember there's single area OSPF, you have multi-area OSPF. Multi-area OSPF, that cuts down CPU and memory usage. When the link status changes, short pathos only needs to run on the routers connected to the link, not the whole topology, and less bandwidth is required to send LSAs because less information is being sent and received between areas. Less bandwidth is required to send LSAs because less information is being sent and received between areas. And last but not least, part 7 out of 7 is our quiz. So 4 questions this quiz. What is the default aging timer for the LSAs? Can you remember? I'll give you. Please pause the video now and then play when you're ready for the answer. Okay, so I hope you had a bit of time to think about this. The answer is 30 minutes. The 30 minutes default aging timer for refloating LSAs. Now, next one. Link state advertisements are packets, true or false? Again, pause the video and please play when you're ready for the answer. Okay, the answer is false. So link state advertisements are not packets. They're data structures that hold topology information. Next question. True or false? 224.0.0.6 is the multicast address for all SPF routers. Is that true or false? Please pause the video now and please play when you're ready. Okay, and the answer is false. So the multicast address for all SPF routers is 224.0.0.5, not 6. Okay, so all SPF routers. So for all SPF routers, it is 224.0.0.5, not 6. So if we just go back to that slide, here we go. So 224.0.0.5, sorry, was here. That's the all OSPF multicast message. So here you can see the designated router sending these packets here to that IP address, multicast IP, reserved multicast IP address 204.0.0.5. And last question: what command would be what command would be used to display brief neighbor information, including router ID? Can't spoil the answer now. So, but okay, just have a think about it, and when you're ready, please play for the answer. Okay, so the answer is show IP OSPF neighbor. Sorry, that kind of got a bit ruined there because I accidentally tapped the screen and it displayed the answer. But yeah, show IP OSPF neighbor is the command that you use to display some brief information, including the router ID, and you'll see this in upcoming videos. So there is more to come, of course. So thank you for watching this video. Apologize for the delay in getting this video out. I'm sorry. I'm going to be doing my best to get content out on time as scheduled, and please stay tuned. There will be more OSPF videos coming soon. So thank you very much for watching.